Hello everyone, my name is Srikumar Ramalingam. I'm an associate professor at the School of Computing in the University of Utah. Prior to joining Utah, I was working as a research scientist in Mitsubishi Electric Research Labs in Boston for about 8 years. For the last few years, I've been working on developing perception and computer vision algorithms for self-driving tasks. Today, I will be giving my views on holistic scene understanding for autonomous driving and the challenges involved. As a vision researcher, what do I have to focus in the future? So first of all, why is autonomous driving hard? Look at an image like this. You have hundreds of cars on a street in New York City. If you want to navigate a car from point A to point B, the first thing that you need to know is the location of the car in the map. How do I plan my path from point A to point B without colliding with other cars? In order to do that, I need to know the surroundings, predict the behavior of my neighbors. And these neighbors, of course, depend on their neighbors' behavior. So it is a recursive thing. So what are the key vision components that are involved in solving this task? This list that I'm going to give you is not exhaustive. The first task is calibration and synchronization of the different sensors on the car. Nowadays, the self-driving cars use a wide variety of sensors like cameras, LiDAR, GPS, sonar, radar. First thing you need to put these sensors in the same geometrical coordinate frame. And you have to synchronize these sensors so that the signals that you get from these different sensors, they come at the same time. Fast depth sensing. Can you get the depth of the nearby car? How far is it with respect to my car? Can you do this with just a stereo camera? Free space and semantic segmentation. First of all, I need to understand where I can navigate without colliding with other cars. I need to know the boundary between cars in the ground, cars in the buildings. This is commonly referred to as a semantic segmentation problem in the vision community. Localization and visual odometry. Precisely getting the location of the car up to centimeter level accuracy is necessary for deciding which lane you are on a road, for example. Visual odometry is the task of finding out the rotation and translation of your car for every second. For high critical objects like cars and pedestrians, it is important to have specialized detection algorithms that can specifically try to get the detection for these objects. So I'll briefly give one of the image-based localization algorithms that we have developed using skylines. If you take an omnidirectional image and try to extract the sky, the line that separates building and sky is called skyline. You can use it as a signature or a fingerprint to get your location. It's pretty unique for different locations in the streets. What you do is using 3D city models of the cities that are available for most cities nowadays, you can synthesize the skylines at different locations using the geometry of these buildings. On the bottom right, you see the synthesized skyline. On the top right, you see the real image. On the top left, you see the location of the car in the aerial image, and the bottom left, you see the matching process. Compared to using other feature object detectors for localization, using Skyline provides more robustness. For example, getting sky in the morning, afternoon, or evening is not that difficult. However, some of these features that like SIFT, they tend to change significantly under different lighting conditions. So the other application that I want to talk about is semantic segmentation. On the image on the left, you see a layered representation of a street view image. When I say layered, the top layer is the sky. The middle one is the building. Slightly below that is car and the other moving vehicles. On the bottom, you have the ground. So you can think of different layers for every image. Using this layered representation of the image, we can get these different segments at a very high speed, at very high accuracy. We were able to get state-of-the-art results on Daimler Urban Dataset for semantic segmentation. Depth estimation using stereo camera is a very classic problem. However, most of these algorithms that are currently available, they don't work at high speed. What we have developed is a stereo algorithm that runs at 100 frames per second using just a single stereo camera on a single CPU thread without using any GPU resources. We believe that for making autonomous driving successful, these inference algorithms have to perform at really high speed, not just 10 frames per second or 20 frames per second, but something of the order of hundreds to 1,000 frames per second. So what are the challenges in autonomous driving? Have we solved the problem? What do we have to solve in order to make this a reality? I'm going to give a few challenges. Of course, this list is not exhaustive. The first one that I would like to point out is many of the vision algorithms that we use right now, they perform really bad. When I say really bad, they perform really bad under nighttime and bad weather conditions. And I think as vision researcher, we should start focusing on this problem right now, and it's very important that we do so immediately. High-speed algorithms for self-driving applications. Many of us are obsessed with getting the best accuracy so that we could be on the top of the table in several benchmarks. But without getting them to sufficient speed, it's not easy to deploy them in practical applications. So getting an algorithm to work at hundreds of frames per second is very important for making critical decisions in self-driving. Inexpensive sensing modalities. So you can't have a car that carries like 500K sensors on it and drives around the city. It's not a feasible model. First of all, we need to develop self-driving cars that are not expensive. In order to do that, we have to use low-cost sensors like cameras and other modalities, not like 100K GPS or 100K LiDAR sensors. But the question is, can we really solve the self-driving task with very cheap sensors? And I think it is possible. Again, the real challenge is many of these datasets that you have, like Kitty or Cityscapes, they are collected in places like Germany, USA. So what we need is a dataset that can look at unstructured roads and unstructured driving conditions, such as having too many two-wheelers and pedestrians on the streets. In order to solve this, we need the dataset. And once we solve the tasks in places like India, I believe that we have completely solved the autonomous driving problem. Thank you for the time, and thanks for listening to my views on self-driving and the challenges involved. Thanks.